So let's now look at the role of energy balance. A negative energy balance appears to be an important factor for reductions in resting metabolic rate. So here we have a change in resting metabolic rate and other characteristics from a period of negative energy balance to a period of energy balance and then a 1-year follow-up, along with the different p-values. So first, let's look at the weight. The participants lose weight when they're in negative energy balance. At week 13, they return to energy balance and they have the same weight. And then at 1 year, they gain a little bit of weight, but they're still lower than baseline. So let's look at what's different. Baseline from week 9, yep, different. Baseline week 13, different. Baseline to 1 year, so it's still significantly lower, but there's no difference between week 13 and week 9. Although there is a difference between week 13 and year 1. Oops. Now let's look at fat-free mass. Fat-free mass also decreases. It increases a little bit, but not significantly at week 13, and we can check that. Oh, it is significant. Huh. I wouldn't have, week 9 versus 13 is different. Okay, well, it's very, very small. And then we see that it remains similar, although, and not significantly different between 1 year and 13. If we look at RMR measured, we see that it starts at around 1800, it drops to around 1600, then it increases a little bit, but let's check. Is week 13 still different from baseline? Yes. So even though they're in energy balance, the energy balance is significantly lower than baseline. If we look at baseline versus 1 year, it is still significantly lower. If we look at our predicted, it's fairly close. In fact, it's easier to look at the measured minus the predicted. The difference between the two is only 4 kcal. But we see that our predicted becomes less accurate in energy balance. It's different by 107 kcals. Then at energy balance, it gets a little bit better, but it's still not near baseline. And it tends to even out at around a year. So we see that at a year, the prediction starts to look better, but it's still significantly different than baseline. So the decrease in energy balance and probably the change in fat-free mass results in a suppressed metabolic rate even a year later. So the important thing to think about is that a diet that restricts calories can result in a suppressed RMR, meaning further dieting will be more difficult. And that's because we see an interaction between intake and energy expenditure. So energy expenditure and intake are not operating independently. They interact with each other, and we can tell because they cross. So this is, again, our resting energy expenditure protocol. Now we'll look a little more at thermic effective food. It's around 10% of our total energy expenditure, so not a lot. To contribute to the thermic effective food, we need to be able to digest and absorb the food. So think about if you had something like celiac disease. you're not able to digest and absorb your food as well. So you'll have a decrease in thermic effect of food. Similarly, if you have, say, insulin resistance, you'll have a lower thermic effect of food. Because you're not able to absorb as many carbohydrates. So things that decrease thermic effect of food: insulin resistance. If glucose can't enter the cell, it can't metabolize it. Age. As we get older, we decrease the amount it takes to metabolize our food. It could be related to decreased physical activity, and it could be related to increased fat storage. We know that physical activity increases the thermic effect of food, and high energy meals increase the thermic effect of food, especially high CHO and high protein compared to high fat. That makes sense, right? Because these two require more energy. High fiber increases the thermic effect of food. So this is the protocol. You use a standard RMR protocol, but you give the person a standardized meal. We can also estimate REE and TEF as 10%. So then we can also add in the cost of daily activity. So this would be like if you had a desk job, if you had maybe a moderate job where you do some heavy lifting, and then heavy would be like a construction or agricultural job. And then there's the energy cost on top of that of physical activity. So one way we can conceptualize physical activity is using a physical activity level, or PAL. Physical activity level is the total energy expenditure divided by resting energy expenditure. And it provides an idea about the duration and intensity, but it may not be independent of body size and lean mass. So think about how we can measure total energy expenditure and resting energy expenditure. So our categories are, if someone's extremely inactive, they'd have a PAL less than 1.4, because remember, it's TEE divided by REE. The closer to 1 equals, that would be completely sedentary. Then, me this week writing lectures, sedentary. Moderately active, this is a construction worker, or a 1-hour run per day. Vigorously active, an agricultural worker, or swimming for 2 hours per day. And extremely active, this would be someone like a competitive cyclist. Think Lance Armstrong. And this can be very accurate if you use doubly labeled water. So again, you'd need doubly labeled water for the total energy expenditure, and think about how you would measure resting energy expenditure. We can also estimate PAL using metabolic equivalents, or METs. These are a numerical value that represent a multiple of the resting metabolic rate for a particular activity. And it can be estimated as the rate of O2 consumption as 3.5 milliliters per kilogram of body weight. So 3.5 ml per kilogram body weight. I always write stuff right where it's about to have a note. So METs have been calculated for a wide range of activities, and they can be looked up in big tables. But please do note that there are individual differences due to body composition, age, gender, and diet. And these METs are only as good as the reported values. So moderate physical activity is 3 to 6 METs. Moderate to vigorous is more than 3, and vigorous is greater than 6. But again, you can check this against our list of PAL. People tend to over-report. So these are the various approximate caloric expenditure per minute for physical activities. And of course, you can always use the body weight planner at niddk.nih.gov. So this is just an example of how we would estimate total energy expenditure. So if we have a 68-year-old white female with elevated lipids, here are her anthropometrics. She walks 2 miles with her husband or friends on Tuesdays and Thursdays and does golfing on Sunday. So we can calculate her REE using Harris-Benedict, but we could also use Mifflin St. Jor. Thermic effect of food, it's around 10%, but mostly we ignore it. Her activity factor, 1.4, really no training. So then we just get to the resting energy expenditure times the activity factor, and that would be around 1,738 kcals per day.